Today I would like to present to you about a very common word that comes in parallel with the 5G and which is commonly known as Wi-Fi 6. So this is looks to be a promising advancement toward having less congested wireless communication, as we will see in the following slide. Myself is Ismael, a Ph.D. candidate under supervision of Professor Mohammed Ibn Gal. So in the following slides, I'll start with an introduction about the progress and about the the appearance of such technology and the devices that have been developed to support from both client side and the access point side. Then I would move to some background about with a few words about spreading spectrum, about the 2.4 and 5 gigahertz frequency spectrums. I'll move forward then with comparing the Wi-Fi 6 with the other IEEE 802.11. And as like many know, the Wi-Fi 6 is following the IEEE 802.11 standards. However, based on the Wi-Fi Alliance naming, they prefer now to use maybe a more appealing names like Wi-Fi 5 and Wi-Fi 6. I will summarize the five main, or the five pillars, what I call the five pillars, or the five main concepts and technologies of Wi-Fi 6. Compared with 5G, what about 5G? Does it replace it? Does it interact with it? Can they work together, coexist together? And I'll conclude with the conclusions and some highlights with highlighting where does IoT stands in that and list the differences. So first, the Wi-Fi 6 is a recent standard. The work began on 2019, and there were some modifications. So if we can see, if we can see that in February, for example, we had the first Wi-Fi 6 supported device from Samsung Galaxy. And just to mention here, in wireless communication, we have two sides. So we have the client side, with the device, and also we have the access point side, and that is following infrastructure-based communication. That is different than the multi-hub, where here we have the client sending directly to the access point, and the access point could schedule and collect the traffic before forwarding it to the internet and to the other layers. So as we can see, so starting from 2019, we are here now in 2020 here. We had a good progress starting from both client sides, and we can see in the top side, and also in the bottom side we can see the access points. So for example, in June, between June and July, we have the first laptops from Intel supporting Wi-Fi 6. From Apple in September 2019, we had the iPhone 11 supports that. With other products from other companies like Microsoft. Also from the access points side point of view, we had the startups starting from the Catalyst 9115 from Cisco, and moving up to the 9124 access points. So this is again, it is a good, it's a good evolution during a short time period, and I would say maybe this is also fostered by the great evolution happening in the 5G, because eventually the business side might be entering here. And having the Wi-Fi technology supporting the 5G and not to be completely replaced. But again, this is my maybe my opinion. We will see later on, based on the other slides, how do I go for that conclusion. So moving forward, let me just summarize some of the concepts and technologies in the wireless communication, and many of you know that, but just maybe a quick refreshment that is related. So for the wireless communication, we use what we call frequency spread spectrum, and there are multiple methods that are used. So the very old ones, for example, direct sequence spread spectrum. So as we can see here, what do we do? So this is the original signal, and what do? We spread the signal over a large spectrum. I think the reason for that started during the wartime, and the point was more of a security, is to be able to hide the original signal, and definitely at the reception side, properly configured like reception side would be able to extract the original signal. That was not the best. I'll show in the next slides. I will map these frequency spread spectrums to the different IEEE standards. After that, we had the frequency hopping spread spectrum, where we have different frequency channels, and what do we do? Both the transmitter and the receiver, they hop between the different channels. And again, the point behind all of that is to be able to send more traffic. So if we can have those multiple channels, and send the traffic, for example, I could start with sending traffic in this channel, then I could hop to another channel, then get back to the channel in the middle. Now we need to bear in mind here that we don't only have one transmitter and one receiver. Normally we have, for example, multiple access points, and we have many clients that they connect between these access points, and they also send and they hand over at sometimes even between the different access points. So just hopping through the frequency helped in increasing the bandwidth, but again it reaches its limitations. Now a more recent technology that is very commonly used in the IEEE standards, the previous ones, is called orthogonal frequency division multiplexing. And what do we do here? We, in addition to having the multiple channels, we subdivide those channels also into multiple sub-channels. And here where we can, the different users can send through those different sub-channels. So this is a very interesting concept, because we don't need to assign a complete channel to the user. So user can take some of those sub-channels and send to them. So if I want to give I want to allow more throughput per user, so then you can definitely assign more channels. But this supported serving and more users, which increase the overall capacity for the network. Now, for the Wi-Fi standard, which is the Wi-Fi 6 standard, it uses an even enhanced version from the OFDM called OFDMA, which I will be showing in the next slides. So before moving forward to the Wi-Fi 6 5 pillars, so I'll just like to shed some light on the very common frequency spectrum. So first of all, there are two kinds of frequency spectrum. One we call unlicensed, and one is licensed. The licensed one are the ones used with the cellular networks, and these normally they are very expensive. And recently they started doing some auctions in even trying to get some very small portion of those spectrum to use it for the mobile networks. Now, on the other hand, Wi-Fi was always built on unlicensed spectrum, in addition to other technologies, and the common name, they called it ISM, or industrial, scientific, and medical spectrums. And these spectrums, they are free, so we don't pay for the spectrum. And what do you pay for when you use them? Is just you pay for an access point, and with a monthly fare, maybe internet connection. If we compare this to the licensed spectrum, that is very cheap. So two common frequency spectrums, they were used in both the Wi-Fi 6 and the previous versions. The first one is the 2.4 gigahertz frequency spectrum. Now, this one is divided into 11 channels in North America, a little slight difference with 13 channels in Japan and 14 in Europe. And we can see just like an approximation for those ones. So as we can see, the width of the channel is 22 megahertz, and the spacing between the different channels is only 5 megahertz. This was good, but it created a problem that we will see also in more detail in what do we call basic service set. So let's say that I have two access points, and these access points, they work in close proximity. So then let's say that I can use, one is working in channel 1, so then I cannot use channel 2, 3, 4, and up to 5, because all of these, they will make interference. And again, based on the concept that we use with wireless communication, which we call carrier sense multiple access collision avoidance, this will create a lot of overall delay. We will see some details later. So then in this case, there was the recommendation from Cisco, for example, that if you have to go for 1 and then use 1, 6, and 11. So this was good solution maybe for the past, but however, currently with a lot of dense deployments, smart city, and a lot of devices, I think that is becoming very congested. So for example, myself, just as an experience at home, like I use myself, for example, the 5 GHz spectrum, and my wife uses the 2.4, and in many times she has a complete disconnection. I tried to use the Wi-Fi analyzer, and those channels are really very crowded. Even if you change, for example, to some other channels like the ones in the middle, so still these channels will be colliding with at some portion with the other commonly used channels by the neighbors. So moving forward, a new spectrum was assigned for those free devices, which is the 5 GHz, and this spectrum goes into 24 channels and divided into 3 sections. There are 3 sections, and this one is the U and I is for National Information Infrastructure from the US standardization. Now, the interesting thing here, so we have 20 megahertz separation between the channels. So if we can see, so the adjacent channels, they still overlap, but they overlap maybe a little on the tails, which makes even the adjacent channels non-interfering. So if you have an access points, you can put, for example, one on 36, and another one you can configure it in 40, and the third one in 44, and they will still be working. They will still be working fine. That is one of the main reasons for the enhancements in the 5 GHz, along with the definitely the higher data rate that could be achieved. So this is mainly but nevertheless, we will see that all the way during the Wi-Fi standards, they don't just go for 5 GHz, because we expect that there are some older devices, and supporting the older devices was older an issue. So we will see, like in the next slide, how then the multiple standards, they try always to have the backward support for the previous ones. So I put this table together, just that summarizing all the IEEE standards all the way. So the original standard, which is 802.11, started sometime in 1997, and the latest one, which is Wi-Fi 6, is called by IEEE 802.11.ax. So again, just to explain, so we have 2 entities that regulate the wireless communication. So the IEEE working group that works toward the 802.11 standard, and the Wi-Fi Alliance. Wi-Fi Alliance is non-profitable organization that helps in spreading the Wi-Fi technology. And what do? They test the devices for interoperability and compatibility, and normally they have a logo. So if those devices are certified by a certain standard, they stamp them, which would greatly help in interoperability. So these are the other names coming from the Wi-Fi Alliance, and again, where we started calling that Wi-Fi 6. And there is another addition which is called Wi-Fi 6 with just a slight variation. I'll come to that. So going back to the beginning, so we started with 802.11 that worked on 2.4 gigahertz frequency spectrum. It used the frequency, the FHSS for the frequency spreading, and it gave us speeds about 2 megabit per second. So that is nothing by today, but during those days, and comparing even to the slow cellular network bandwidth and the data rates, so this was something it's still acceptable. Now, after that, there were two ratifications for the original standard that came in and after 2 years, and they came with two standards. One is the 802.11a and the .11b. The .11a worked on the 5 gigahertz frequency spectrum. It gave us better speeds with 54 megabit per second. However, there was a limitation in this standard that it did not do good wall penetration, and that was of the limitations, and that's why this led the people to still have the other version, which is B, with 2.4 megahertz. So this increased a little compared to the original one, which was working on the 2.4. So increased the data rate from 2 megabit per second to 11 megabit per second, and resolve the challenge with the wall penetration and the range. Now the B was more common, by the way, due to this limitation. The .11b used the DSS for the frequency spectrum. In 2003, then there was another revision, another version that you started using the orthogonal frequency division multiplexing, and then it granted us a 54 megabit per second, which was the same data rate by the .11a standard. However, definitely this has the advantages of the higher range and avoiding the challenge with the wall penetration. So in 2009, we had the .11n standard, and that worked both in 2.4 and 5 gigahertz. This gives a good support for all the previous, so it can support the devices in any of the previous standards, including the original A and B. It gave us a range of around 70 meters. Still, that's not a great maybe compared to the cellular, but again compared to the cheap license that was for indoor communication, is still very good. Data rates up to 600 megabit per second. Here we started using the multiple MIMO, the multiple antenna with the multiple antennas. In 2013, we have an interesting standard, and which is, by the way, did very well, which is the .11ac, and was used to be expanded and enhanced to give us the Wi-Fi 6, and that what are we talking about today? The AC standard uses also the OFDM, but again it used the multi-user MIMO, and it was not mandatory. So then in this case we can see that there is a range of data channels, so there are multiple, so you can work on 1.3 and maximum of 6.9 gigabit per second. The latest one that we call .11ax is the Wi-Fi 6, and that supported actually also both 2.4 and 5 gigahertz. And there is another addition that is started in 2020, which we call 6E, and that one it works in a new frequency spectrum. It is a very clean spectrum in the 6 gigahertz. That I think it was licensed in the US, and there are some devices that are working or started to be working with the spectrum. Now, this technology uses similar technology to the OFDM, but is still more enhanced. We call it orthogonal frequency division, multiple access, and I'll show on the next slide what is the difference between these two. The data rates is comparable to 5G. So like I saw 9.6 gigabit per second, even at some papers I saw 12 gigabit per second, and with using this is the maximum if you are using the support up to 8 antennas. The interesting thing here in the AX also, it provides also good power efficiency using some of the techniques which will make it very efficient for IoT. So this is some more or less like a general comparison to see where does the Wi-Fi 6 stands and how does it compare with the previous IEEE 802.11 standards, and some estimation about the speeds. One word I would like to mention here before moving to the pillars, that these speeds, by the way, are theoretical, and we don't necessarily get exactly. So if I'm saying 2 megabit per second, that doesn't, it depends on how many users I have in the shared media, and that does not mean that every single user will have those 2 megabit per second. So there are multiple users, they will there will be a contention for the bandwidth, and then based on that there will be a reduction. But the interesting thing that we will see in Wi-Fi 6, we are going in this one, we are going toward a more organized, contention-free. So the target is to reach contention-free and more stable, more organized spectrum, and we will see how is that happening. So I summarized the 5 pillars for Wi-Fi 6 in the following technologies. So the OFDMA, orthogonal frequency division multiple access. The target wake time, that is for sleep scheduling. BSS Coloring, how do we help in resolving the basic surface set problem, and if we have multiple access points in a close proximity. And also we have higher modulation with the QAM, and we use also multi-user MIMO. So just to mention that some of these technologies were used in the previous standards, which is the AC. So for example, the multi-user MIMO was there, but here the multi-user MIMO with the OFDMA together, these ones, they mainly made like a great breakthrough in having such kind of better organized and wireless communication. Is the difference between the OFDM and the OFDMA? So, if we can see, these are the different channels that we showed before in the frequency spreading spectrum. So here we have the time, and vertically we have the different frequencies, the different channels. So in OFDM, what do? We divide, as mentioned, we divide the spectrum into multiple subcarriers. And in every time slot, which is, let's say, every time slot, we assign it for a user. So in a specific time slot, a single user will take the whole subcarrier, all the subcarriers, and send the traffic. In OFDMA, what do? They went one step more, and they divided even the y-axis with the frequency with the channel, with the subcarriers themselves, into smaller units. We call them resource units. So then in this case, if I have, for example, let's say a user who's doing the streaming video transmission with high quality, so I can assign him the whole subcarrier channel. But for example, if I have some IoT devices, they are sending chunks of data and they don't need to have the whole thing, so they can just wake up and transmit the data. So I can, for example, schedule them to sleep and then assign them some resource blocks to collect their data. So that was the main difference, that together with the multi-user MIMO helped in serving multiple users. So for example, we can see on the right side here that these are the resource units, that is one sub-channel, and I have different resource units. So for example, here I'm serving multiple users. So we can think in that in the same time slot, I have a track, and rather than just putting all the components for one user and sending it, even if I might have even some empty spaces, so I'll send it and I'll send all the parts for that user, so I can put the traffic from multiple users in one large packet and send it together. So this might not be excellent in case we have some clients with very high data traffic, but it really helped in supporting more users and also in having more consistent traffic. Another feature here that we can see, that there is something which this will work also with the TWT, that here we have the access, it's an access point centric rather than client centric. So in the previous versions, we had the client, it tried to it tried to announce itself and tried to get the wireless channel. Hi, I want to send, then the access point, if there's no one sending, it will give him the grant, we call it clear to send, and then the client will start transmitting. Here in this case, with the wake up and the sleep scheduling, the access point schedules the transmission and send wakes for the wake ups for the devices to send, which we'll see maybe in some visualization in the next slide. So this is mainly the main difference using the frequency. This greatly enhanced the spectral efficiency. The other feature is target wake time. So as introduced, so these are the different users. So what does the access point schedules the transmission rather than the client's content and the try to content for the transmission. So just in very general, I don't want to go in the very details, but generally there are some the beacons which are the normal periodic packets with the wireless transmission. But then there are some trigger messages that will trigger the different devices, and there are a lot of details in behind. Like I saw in the papers, a lot of things about the antenna designs, about for example collecting some traffics about the channel conditions from the users to try to help in doing better scheduling. So the devices they sleep, they trigger to communication. One of the interesting thing, in addition to the power consumption here, is eliminating interference. And as I said, interference is a great killer for the overall network bandwidth. Because again the technology in the Wi-Fi it works in that users announce themselves that I want to send, which is trying to get clear to send, called carrier sense. So they sense that channel, and then multiple access, all they access it. And then collision avoidance. If I notice that there is some kind of a signal that will be for an interference of the channel, then I will assume that some users are sending. So what they will do, the devices will make a random back off, and they will wait. After that time, they will try to sense again. So then if we have more devices, this will make a lot of back offs, which mean a lot of delay and reducing the overall throughput. Another problem that the Wi-Fi 6 addresses is what do we call BSS coloring. And just to show an example, so let's say that we have two access points. So two access points, they are in close proximity, so they have to overlap, and this overlapping is to support roaming. If I have my laptop or my mobile, and this is one room, I'm moving to the hallway, and while I'm moving, if this overlapping is not there, I will like suffer from some kind of disconnection. So what do they do? They do, like previously, I remember even the Cisco Turkey Academy, they used to mention something about 30%. Recently, I noticed they just reduce it to 10 to 15%, maybe with the enhancements with the antennas and with the standards. But still, there is some kind of there is an overlapping. Now, this overlapping, the problem it reduces first of all it makes more interference. So let's say that I have a device which is here in this overlapped area. So this device receives. If I try to send, I need to sense the channel. So if there is any device sending on the left basic service set area, so then I have to back off. And if there is any device also sending on the right basic service set, also I have to back off. So this is the problem. And again, it reduces the overall throughput. The same thing if the device which is lying here try to send, so then again it will create an interference for both basic service set areas. So what do they do here? They follow something like they try to add some information about the channel conditions, and if they call it color code, and if those channels are busy, then based on the channel information, then the access points will avoid. For example, if I'm based on those information, I know that some channels are busy, so then I would avoid like sitting and doing my transition in those channels. Now this one is maybe someone could say that we know that even the access points, even in the previous ones, they were able to communicate and set different channels. But again, in this kind of technology, even the access points, they have more active communication between each other to properly divide the frequency spectrum and greatly reduce the interference and the congestion. The quadrature amplitude modulation, very well known concept. So just to make it very simple, what do we do here? Like when we send a signal, so first of all, we send orthogonal signals, which are phased by 90 degrees, so they don't overlap. And when we send those signals, we can change it in two things. So first of all, we can change in the phase. So I have the 0, 90, 100, 270, and up to 360. And also we can change the amplitude. The amplitude is not shown here, but it is shown here on the right side. Based on that, I can have multiple states, and I can send different bits. So for example, this one shows that we call 16 equam, and in the 16 equam, I can send 4 bits in one sample. And just to show, so let's say here, so if this is the amplitude, so if this one, for example, I'm in 25% amplitude, and my phase is 225 degrees, so then I am in 110. If I went to the full amplitude, then I will be 111. Again, if I change the phase to some other phase, for example, the 90, then I'll be going, for example, for other samples. So that's, and like there was a nice animation, like, so this one for the transmitter and the receiver, what do? They keep rotating, for example, between the amplitude. So again, I change the phase, then I change the amplitude, and based on that, I'll be able to decode the different bits. And that's the whole thing about wireless communication, is to eventually be able to send my data through zeros and ones. So this is a very simple one, but to link to our technology, the previous standard, which is 802.11 AC, uses a 256 QAM, so which means I can send 8 bits per symbol rather than 4 bits. Now the latest one, which is the AX standard, is 1024 QAM, which means I can send 10 bits per sample, and definitely when we send more bits per sample, which means I'll be increasing the overall data rate. Definitely, this is not like it is not a straightforward, and when increasing the modulation, like all the technology has to come together, and we have to support, and we don't want to make the interfering between the channels to each other. Another pillar for the Wi-Fi 6, what we call multi-user MIMO, and again, as I mentioned, this was used in the previous standard, which is the AC, and used also with the AX, but with the OFDMA, it is greatly helpful. So here with the so we have multiple antennas, and these are the different streams. So for the single user MIMO, so the whole antenna streams are focused toward one user at a time. This might help in reducing the interference, and also might help in increasing the overall throughput for a single user. Now, in the multi-user MIMO, what do? We use the like the most advanced beamforming and antenna designs, and then based on that, we are able to send different streams. So, for example, in this example, this is a laptop. It has a lot of traffic. Maybe it's streaming some kind of a YouTube match or something. So then I can assign 2 streams for the laptop, and then I can assign another stream for the other 2 devices. So this is so first of all, this is configurable, and even if I want to assign all the streams to one user, I still can do that. But the idea that I have the option to serve multiple users simultaneously, so this will increase the overall capacity, and also it will serve more users, and that is very interesting in environment where we have what do we call dense traffic, like stadiums. So you don't want, for example, to serve some users while the others are going in what do we call starvation. So then in this case, even with the different access points, so the different access points, they efficiently divide the overall frequency spectrum, and then even the single access point can use the latest advancements in the MIMO to even pull the traffic in from multiple users at the same time. So after that, so this is a summary of the main features of the Wi-Fi. So first of all, we are again going into what do I call more organized wireless communication. It's called deterministic communication compared to best effort. Before it was best effort, try to send. If there is no channel, what do? You just back off. So here we are going for more deterministic, where I can schedule the devices to send. I can even beamform the antennas to serve the specific users and multiples at the same time. So definitely we have expectations are 4 times increased compared to the the previous standard, which is AX. So we're talking about data rate of 9.6 gigabit per second if using all the antennas, but it is 1.2 gigabit per second for single antenna. Higher spectral efficiency, support for multiple, for even the previous legacy devices. The interesting thing also, there's the 6E edition, the Wi-Fi 6E edition, which works in the 6 gigahertz. And I just read one white paper from Cisco that it looks very promising because it's a very clean, and they gave even a wider spectrum compared to the previous ones. We spoke about the overall reduced power consumption, also the which will be very suitable for IoT devices, the overall higher modulation. And again, this was always a challenge for both for IoT and for what do we call dense traffic transmission. Wherever you have, for example, a football match with a stadium, and you don't want to deploy a lot of access points just for these ideas. So then, based on those devices, you deploy less access point, but using those technologies, you can still support all the users. There is another interesting also feature for the Wi-Fi 6 that it supports the very recent, like even with the COVID-19 and people, they are blocked at home. So we see a lot of video streaming. We see what do we call 4K and 8K video streaming. These are more of resolution, so higher resolutions, the augmented reality and the virtual reality. So these are the video streaming and the latest enhancement of video streaming. I didn't see autonomous vehicles mentioned somewhere, maybe because it's a critical application, but maybe I'll just shed some light on that in the next slide when I talk about the interaction with the 5G. So this is the big question now. So is Wi-Fi 6 replacing 5G? Is 5G better? Is 6G better? And based on what I read, I think the best thing is just they need to coexist together. So there are some use cases. For example, in indoor networks, generally homes and offices, Wi-Fi 6 would be more suitable. And remembering that we are talking about a free unlicensed spectrum. So definitely, like when for 5G, we are saying that we are reaching this kind, which is 1 millisecond and 10 gigabit per second. But this is eventually a licensed spectrum. So even myself in my mobile, I have 9 gigabytes from Fido, and I thought it is a lot. But even opening maybe some meetings, as I noticed that the traffic goes degrades quickly, even if you are including even the headers on those traffic. So the idea, so the conclusion here for indoor and offices, 6G would be very suitable, would be high efficient. Also, if we have dense traffic like stadiums, like convention centers. On the other hand, 5G, it would be good for high mobility. So for example, if we are driving outside, we are away from the smart city, or even we have a high level of mobility, then 5G would be better. In case of mobility, maybe within a smart city, I would say, and within inhabited areas, so then both of them could work together. In my conclusions, I just would like to highlight. So first of all, Wi-Fi 6 is really good for IoT, and in reality, the power consumption for the TWT, it used from one of the other standards. I don't have the exact number on top of my that's called Hello, and in that one where it introduced the concept to schedule the sending and put the devices on. So this greatly reduces the power consumption. In some studies, it mentions that 30 or even more % with the sleep-wake and scheduling. In adding that is on the top of reducing the interference. So both technologies, they will coexist, the Wi-Fi 6 and the 5G. I think we need to have to create some room, even of cooperation, rather than competition, and they create some kind of smooth handovers that will greatly support mobility. So if I'm even streaming an 8K video and I'm inside home, then the moment I start just stepping outside, so automatically it will hand over to 5G, and then where we will have what do we call the seamless and uninterruptible communication. The last two points, like again, I mentioned during the discussion that here we are using the unlicensed frequency spectrum, which means that mostly in the Wi-Fi it is free compared to the licensed spectrum, and also it creates for us a great support for the latest video like high quality video, and also for the dense traffic communication. And these are a list of references that I used. I refer to multiple references, and I refer to a white paper from Cisco, and even to the Cisco Networking Academy, the course of switching, routing, and wireless essentials. Just to mention that one of the challenges that I even find that there are not a lot of complete papers of even maybe a surveys that details the Wi-Fi 6 and the related technology, maybe because the Wi-Fi 6 is not just something that's brand new and it's building on the previous technology, but most of the references, there were a lot of news, a lot of blogging, a lot of promises, and there were a few papers. Some of them they focused on even the antenna design, on how to design antennas and smart antennas towards supporting the overall objective. So this is my presentation, and I would be pleased to take questions.